Well, welcome to Lesson 5 of Chapter 8. This is the last section in this chapter, and this section is on vectors. A vector is anything that has both a size or a magnitude and a direction. Things like forces or different electric fields, different things. There's a whole bunch of different things that are vector quantities. Gravity is an example of a vector quantity. It has a magnitude of 9.81 meters per second squared, and its direction is toward the center of the earth. So vectors are things with a magnitude and a direction. So how do we use vectors, and what are they exactly? It's basically a ray. Okay, geometrically it's what we would call a ray, and the vector has an initial point K and a terminal point W. Okay, so your ray or your vector always goes from an initial point to a terminal point, and the direction corresponds to the direction in which the arrow is pointing. The magnitude is just the length of the arrow. And then we will also represent vectors using an XY notation with, instead of parentheses, we'll use these caret symbols inside to represent that it's a vector in the coordinate plane, where X is the X coordinate and Y is the Y coordinate in the coordinate plane. So we'll take a look at that in a few slides ahead here. Describing a vector. How can we describe the vector right here in red? How can we describe that as an ordered pair to the nearest tenth? Well, we know its length is 65 units long, and we know its direction, but we want to be able to write that as an XY ordered pair. So the first thing we need to do is to go ahead and draw the vector in here, and then we need to draw the two dashed lines that show us how to get to that vector. So you're going to start with from the terminal point down here, L, and draw a straight line back to the x-axis, and then a straight line on the x-axis back to the initial point, so that you will always make a right triangle. Then we want to be able to find what x and y are. Well, if we want to find x, if you think about this, if we want to find the value of x, what we need to do is we need to set up one of our trig functions that we've been talking about, and we know the hypotenuse and we have the adjacent side. So adjacent and hypotenuse is the cosine function, right? So the cosine of the angle is equal to the adjacent over the hypotenuse of 65, and that's exactly what we're going to do. Okay, so the cosine ratio, cosine 50 is x over 65. We've talked about how to solve these, and so using our calculator we get about 41.8 to the nearest tenth. So what trig function would you use to get the y coordinate then? This would be the opposite side and the hypotenuse, and that is the sine function. So in the same way that we did the cosine function, we're going to use the sine function. Sine of the angle is the opposite over the hypotenuse, and then multiplying both sides by 65, we get y equals 65 sine of 50 to the nearest tenth. It's about 50, well, 49.8, I guess, to the nearest tenth. So the terminal point, this is in the fourth quadrant, okay? It's in the fourth quadrant, and I might need to review that with you just to make sure you remember what the quadrants are. So in our XY coordinate plane, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. This is down here in quadrant 4. Okay, so since we are in the fourth quadrant, we know that the Y coordinate is negative in the fourth quadrant. So to represent our vector, we have a positive X value, it goes to the right, and a negative y value. So we would have 41.8 for the x value and a y value of 49.8 that's negative. Here's one for you to try, very similar to the one on the last page. Please pause the video and try this one on your own. Alright, hope you gave that a try. This is a good practice for you. I know this is difficult at first. When we try new things, they're sometimes complicated, but as we get more and more practice, it becomes easier and easier to do. So we have a vector whose magnitude is 51, and its direction is 55 degrees. So the first thing we want to do is write what our trig functions would be, and the first thing I want to do here is show you to draw that line down vertically. This is not going to be a very straight line here. I should do this. Let me Let me try something else here. I have a way to draw straight lines much better than that. So let's do this. We'll draw this straight line right down there to our x-axis. Much, much better. So make sure you draw that straight line down and then figure out what you want to do for your x and y coordinates. Now this would be on my y coordinate. This is on the x-axis. This would be my x coordinate. So if I'm looking for the x-coordinate, that is the adjacent side, and we have the hypotenuse, which is 51, which is my cosine function. Okay, the cosine of the angle is the adjacent side over the hypotenuse. Multiplying both sides by 51, and then solving for x, we get 29.3. So again, for the y function now, this is the opposite side, so we want the sine function. Multiplying by 51 and then solving, we get y equals 41.8. Well, can you tell here which of these variables, if either of them, are either of them negative? Well, in quadrant 2, x is negative, right? We go to the left, which is a negative direction for x, and then we go up, which is a positive direction for y. So in this case, x is going to be negative and y is positive, and our vector is represented as such. In many applications, you use compass directions north, south, east, and west to describe the vector, so we're going to practice this a little bit. What is the direction of each vector using compass directions? Well, this vector right here is in quadrant 4, and it is below the east-west line, and it's to the south, and they tell us it's 25 degrees, so we say that it's 25 degrees south of the direction east. How about over here? This one's almost north, but it goes east. So this is 35 degrees east of north. Okay, so those might take a little practice to get used to how to write those. Finding the magnitude and direction of a vector. Let's say an airplane lands 40 kilometers west and 25 kilometers south from where it took off. And here is how we would represent that as a vector. Okay, west and south are both negative directions. Okay, west is always negative, south is negative, north is positive, and east is positive. So keep that in mind when you're writing your vectors. What are the approximate magnitude and direction of its flight vector? So we want to know how long is this red vector and what is x in degrees. Okay, well the way we're going to do that, we're going to have to use the Pythagorean theorem, or you could use the distance formula if you want to think of it that way. Your book used the distance formula. I think it's just as easy to say the Pythagorean theorem where your x distance was 40 and your y distance is 25. So you do 40 squared plus 25 squared square root, and you get the same answer, 47.2. Now how about x? Remember, anytime we're finding an angle measure, we're using an inverse trig function. So first of all, let's set up our tangent function. That would be the opposite over the adjacent. So remember, the opposite side is going to be 25 right here, and the adjacent side up here is going to be 40 units long. So our tangent function will be opposite over adjacent, which is 25 over 40. So the inverse tangent of that will give us our angle, which is 32 degrees. So to the nearest tenth, the airplane flew about 47 kilometers, 47.2 to the nearest tenth, and 32 degrees, and the direction would be south of west. South of west. Here's another one for you to try. Let's say an airplane lands at 246 miles east and 76 miles north from where it took off. What are the approximate magnitude and direction of its flight vector? So you're looking for the magnitude of the red vector and what the angle theta is between the x-axis and that vector. Go ahead and pause the video and work on this one, and I'll give you the answer when you come back. All right, let's take a look at this one. So I have drawn in what your x and y components are. So the easiest way to figure out what the magnitude of the resultant is just to go ahead and use the Pythagorean theorem. 246 squared, right, plus 76 squared equals our resultant. Let's just call it r, okay? Equals r squared. That stands for resultant. So what do we get? 246 squared gives us a big number, 60516. And then 76 squared gives us another big number, 5776. And that's equal to r squared. So now if we add those two together, I get, let's see, 66,292. And that's equal to r squared, but now we need to take the square root of both sides, right? To get rid of the squared, these cancel, and I'm just left with r is equal to the square root of that answer. Yeah, that's 257.5. If I've done my calculations correctly. Remember, if you ever find a mistake for me in here in these videos, be sure to let me know so that I can correct those. So it looks like our magnitude is 257.5. Now we just need to find theta. Okay, we're looking for this angle right here. And that angle, we have the opposite and adjacent, which is our tangent function. But whenever we're looking for an angle measure, we're going to use the inverse tangent function. And the opposite is 76, the adjacent is 246. So we punch that into our calculator, the inverse tangent of 76 divided by 246. That gives us about 17 degrees. Okay, so 17 degrees, here's our magnitude. What's our direction of our vector? It's 17 degrees, and our direction, this is east, and it's a little bit north of that, so we would say north of east, using our north, south, east, west directions. All right, some notation for you. We use a single lowercase letter, and it's usually in boldface type. So you'll notice that whenever we have a vector, it's in boldface. So down here you see these are vectors. And it's like a half of an arrow above that to give it the notation of a vector. That's how we represent a vector using mathematical symbols. And here's a map that shows somebody took a trip from Albuquerque, New Mexico up to Salt Lake City, Utah. And they took that trip by way of Flagstaff, Arizona. So they went to Flagstaff, and then they went to Salt Lake City, and then the resultant vector is W, which is the sum of those two vectors, U and V. So that brings us to a property for adding vectors. And vectors can be added mathematically or algebraically just by adding their corresponding x and y coordinates. So let's take a look at how to do that. So let's suppose we have vectors A and C, shown in the picture in red, and their coordinates are -4, -3, and 1, -2. What's the resultant E of the two vectors as an ordered pair? And draw the resultant. Now I'm going to show you a couple of different things. I'm going to show you algebraically how to do this, and then I'm also going to show you graphically how we do that below. So algebraically, we want to write the vector addition equation where E is equal to the sum of A and C. And now just substitute in what their coordinates are for A and for C. And then when we add them together, we're going to add the x coordinates and the y coordinates. So remember, we're adding -4 to 1. And then we're also adding -3 to -2. And I know you can do this in your head, but I'm going to show you anyway. So -4 plus 1 gives us -3. -3 minus 2 is -5. And that's how we would write the resultant. So that's algebraically what we would do. What we would do graphically, this is very, very important, so pay attention to this. The method that we use is called the tip to tail. So tip to tail method. And that's how we add vectors graphically. And what you do is, the first step is you go ahead and you draw your first vector A. And your second step, at the end or at the terminal point of A, you redraw your vector C, okay, where its initial side starts at the tail, or at the tip. Its tail is at the tip of the first vector. And then we draw that vector in. The resultant always goes from the initial point to the final terminal point. So that is the step 3, is to go ahead and draw the resultant vector. That's the one in blue. So there's what this vector -3, -5 would look like as a resultant. Here's one for you to try. Go ahead and do that algebraically, and then see if you can do it graphically as well. All right, so algebraically, I'll just demonstrate this one algebraically. We're going to get 2 plus a -4 for our x coordinate, and our y coordinate will be 3 plus a -2. So we end up with a -2 for our x-coordinate and a +1 for our y-coordinate. A vector sum can show what happens when vectors occur in sequence, as in the airplane problem that we had on the previous page, or it can also show what happens when things happen at the same time. For instance, suppose we have a canoe, and the canoe wants to travel in this direction as this red vector here, but it hits a current. There's a current in the water because it's windy out someday, so that current is going to throw the canoe off course, and the resultant in blue here is the direction that the canoe actually travels. Those can be represented using vectors. So here's a problem. Let's suppose your friend invites you to go boating on the river, and the speed of the boat that you're using in still water is 35 miles per hour is how fast it can go, but the river is flowing 8 miles per hour directly south. If the boat heads directly west, we want to know what is the boat's approximate resultant speed and direction. So that's in blue here, the vector c. Well, the magnitude's easy enough to find, right? We know how to do that using the Pythagorean theorem. So we're going to go ahead and plug those in. C squared equals a squared plus b squared. And then calculating that, we get an approximate distance or magnitude for the resultant vector of 35.9 to the nearest tenth. And then we need to figure out what is that angle x up there. Well, we have the opposite side and we have the adjacent side. So that would be our trig function tangent, right? So the tangent ratio says the tangent of x is equal to opposite of 8 over the adjacent of 35. And then remember, we have to use the inverse tangent to get rid of that tangent function. So x is equal to the angle whose tangent is 8/35. And on our calculator, that's about 12.9 degrees. So our speed up here is about 36 miles an hour to the nearest whole number. Its direction is about 13 degrees, and the direction is south of west. Okay, this direction would be west, and it's a little bit south of that. Here is your lesson check. Please have these ready to turn in when you get to class tomorrow. We'll see you next time.